Assalamualaikum warahmatullahi wabarakatuh and good day everybody. So now, Alhamdulillah, we end our lecture in this subject of static and dynamics. This chapter is your final chapter, chapter number 11 in the Engineering Mechanics Dynamic written by R.C. Hibbeler. This chapter, linear impulse momentum, is in chapter number 4. Okay, but in our subject static and dynamics, this chapter will be chapter number 11. So you have learned so far 10 chapter of static and also dynamics. So now hopefully they have 2 video in this chapter. So the principle of linear impulse momentum, the objective of this this topic is you should be able to calculate linear momentum of particle and linear impulse of force, and also apply the principle of linear impulse and momentum. Okay, the principle of linear impulse and momentum in vector form can be written as the mv1 plus the total summation for force multiplied by dt is from the t2 to t1 is equal to m multiplied by v2. v1 is initial velocity, so v2 is final velocity. So particles initial momentum plus the sum of all the impulse applied from t1 to t2 is equal to particles final momentum. So mv1 is initial momentum, mv2 is a final momentum. So the two momentum diagram is indicate direction and momentum, magnitude of the particles initial and final momentum mv1 and mv2. So it can be illustrate in this diagram. For example, an initial momentum diagram, for example, this object moving to the right, for example. So plus they have the force applied to the objects during the interval t2 t1 from t1 to t2. So given this direction, so the impulse diagram, this is the impulse diagram, so it's equal for final momentum diagram. So this one is the final momentum diagram, so the mass multiplied by v2 in this direction. The impulse diagram is similar to free body diagram but include the time duration of the force acting on the particle. Okay, so impulse and momentum, because due to the rectangular component, the scalar equation, since the principle of linear impulse and momentum is a vector equation, it can be resolved into x, y, z component. So we have the linear impulse and momentum in x direction. This one in x direction, you can see here all the component in x direction. This one is a component in y direction, you can see here all the component y direction, and finally all in z direction. The scalar equation provides a convenient means for applying the principle of linear impulse and momentum once the velocity of force vector has been resolved into x, y, z components. Okay, how we want to solve the problem? First one, establish the x, y, z coordinate system. Our reference plane is based on x, y, z. Draw the particle's free body diagram and establish the direction of particle initial and final velocity. So in order to draw the impulse and momentum diagram for a particle, we show the linear momentum and force impulse vector. So then we are resolve the force and velocity respect x, y, and z, and apply the principle of linear impulse and momentum using the scalar form. Finally, force as a function of time must be integrated to obtain the impulse. So if a force is constant, so this impulse is the product of force, magnitude, and time interval over which it is at. So if the force is constant, so just an impulse is just product of, you just multiply the force magnitude multiplied by the time interval. Okay, we can see here one example. So we have the 0.5 kilogram ball strike the rough ground and rebounds back. So v1 here, initial velocity v1, so bounce here, strike here and it rebounds. And neglect the ball's weight during the time it impacts ground. Find the magnitude of impulse force exerted on the ball. So our plan is to draw the momentum and impulse diagram of the ball and fill the space, and they apply the principle to determine the impulsive forces. Okay, so the impulse momentum can be drawn as, this one is the initial momentum, the velocity with the 45 degree. This one is the impulse diagram. So we have the force, we have the normal force, we have the weight, and equal to the final momentum. So the impulse caused by ball weights and the normal force can be neglected because their magnitude are very small as compared to the impulse from the ground. So this one we are neglecting only the force dt, the impulsive force here. Okay, so we are applying the principle of momentum. So this one all the principle of momentum. So now we want to establish, because we are established in x and y z reference, this one we are resolving to x component. So you can see here x component is I, and also the g component is y. So you're resolving the 25 cos 45, this one the velocity, the initial velocity. So 25 you resolve into x and y, 10 you resolve into x and y. For the initial momentum 45 degree, final momentum 30 degree. So you can see here, so the 25 multiplied cos 45 minus 25 sin 45, because y negative, because this one the ball is a strike going down up, so downward is a negative for y. So and then this one is the to the right is a positive y. So plus impulsive force, so then it's equal to the final momentum. So 10 multiplied with cos 30 is the positive x direction, then 10 sin 30 is a positive y direction. So impulsive force vector is this one. We can this one we leave the impulsive force at the left side, so this something to the right side. So we have here, so magnitude of impulsive force we can determine by the square root of product of the component of x square plus the component of y square. So we have 5.2 Newton dot second. This is by the impulsive force. Okay, what we conservation of linear momentum for system particle. So now we have moved to a new topic, another topic in linear momentum. So we have the conservation of linear momentum. So you should be to understand the condition for conservation of momentum. So what be the condition? Is the sum, when the sum of external force acting on the system is subject to 0. So if we are referring the principle of linear impulse momentum, we have the plus the initial momentum plus the impulsive force equal to final momentum. So if impulsive force is equal to 0, so initial momentum is equal to final momentum. So this equation is referred to as a conservation of linear momentum. So conservation of linear momentum is often applied when the particles collide or interact. When particle expel only impulsive force cause a change of linear momentum. So simply they have example, the sledgehammer here apply on impulsive force to the stick. The weight of the stick here considered negligible or non-impulsive as compared to the force of the sledgehammer. So also provided the stick is driven into soft ground with little resistance, the impulse of the ground acting on the stick is considered also the non-impulsive. So we can see here one example. So two rail car with mass of ma is this one the rail car M, the rail car, this one rail B. So 20 megagram for A, 50 megagram for B. So velocity as shown is a figure 3 meter per second for rail A, 1.5 meter per second for rail B. The speed of find the speed of car A after collision if the car collide and rebound so such that the B move to the right with the speed 2 meter per second. So A and B will move to the right. The speed of the car A, when the car collide and rebound such that the B move to the right. So B is moving to the right. So also find the average impulsive force between the car if the collision takes in 0.5 seconds. So friends, we are need to using the conservation of linear momentum to find the velocity of the car after collision. All internal impulse are cancelled. Then use the principle of linear momentum and impulse to find impulsive force by looking at only one car. Okay, so conservation of linear momentum in the x direction. So A moving to the right. So here is E is a positive 3. So B is going to the left. You can see here negative 1.5. VA2, we are not sure. We didn't know the what is VA2. VB2 is 2 meter per second to the right. So here we put the mass of A, mass for B, despite as a mass A, mass B here. So finally we get the final velocity for the rail A. So it is given by 0.375 to the right because we get the positive value. So how to get the impulsive force? So impulse and momentum, impulse and momentum. So using this equation, we only taken about only one rail car only, but this the initial momentum to the right, and so final momentum also to the right. So we have the force. This one force given by the rail B towards to the rail A. So the force is to the left. So we have so negative direction of the impulsive force. So we have using this equation, finally we can determine the final impulsive force by the 15,500 Newton. So finally, the average force given by the 52,500 is equal to average force multiplied by the time taken take place, 0.5 second. So whereby the average force is 1,105 kilonewton. Okay, I think we stop here for this topic. So we are continue our final chapter in the next session. We see you again. Thank you.